Okay, so let's start. Good morning, everybody. Welcome to this workshop, to this FF4EuroHPC third workshop. So, and thanks for attending this workshop. You know that the second round of experiments selected for the FF4EuroHPC are closed now by end of May. And we are organizing 4 workshops to allow experiment partners to present their realization and the solutions they developed in the framework of this project. So this is the third session of workshop, and will include experiments using machine learning and deep learning for various sectors of the industry. So we will follow this agenda. So starting by this welcome and introduction will be made by my colleague Tina, and then we have a presentation made by Francesco Sabbarese and Valentina Senatori from Youbiquo concerning HPC for hand-gested dataset generation and deep learning training for detection and tracking. The second presentation will be made by Toralf from Pumacy and concerns high-performance reliability computing. The third presentation will be made by Paolo Mazzucchelli from Aresys and concerns remote sensing and HPC for smarter water cycle management. The fourth presentation will be made by Marjan Gusev from Innovation and will deal with real-time heart monitoring of thousands of patients. And the last presentation will be made by Alessandra Truppi from TCT Nanotech and concerns multi-phase modeling of nanofluid hydronic systems. So a session of 5 minutes for question and answers is planned at the end of each presentation. So please, if you want to ask a question, make it by the question section, or you can ask it to my colleague. Ask my colleague to have the micro to ask the question by yourself. So I let the floor now to my colleague Tina to introduce the FF4EuroHPC project. Thank you. Tina, please.
Hi, welcome everybody. So my name is Tina Marz, and I'm the FF4EuroHPC communication lead. And before we are actually heading to the presentation of the success stories, I would just like to give you a brief introduction into the project itself. So the FF4EuroHPC project is a successor of previous Fortissimo projects, is H2020 research project supported by EuroHPC GU. It is coordinated by HLRS and supported by 5 other partners, so Arctur, Sesga, Cineka, Scapos, and Teratech. The project itself aims to, let's say, promote the use of HPC, AI, and other related technologies for business purposes. So how to implement technologies to become more innovative, to shift the potential of industry, of course, on focus on the European industry to become more competitive. Furthermore, we are also facilitating the access to the HPC-based infrastructures and services. So also one of our partners could, let's say, try and reaching out to some of the EuroHPC state-of-the-art infrastructures. Then we are, of course, aiming to foster wider innovation while exchanging best practices and use cases, also the knowledge, all these experiments provided with, let's say, promoting the success stories in a way that you will hear today. So how to use the technology for business challenges, address them properly, develop nice solutions, and then actually gaining some business impacts and some good results. They will be actually presented in the next steps. And lastly, of course, by supporting the experiment partners with funding, the project is, let's say, lowering the barriers that SMEs actually face at the beginning of their journey and offer them some kind of opportunity to exploit new business opportunities and enter, of course, new markets. As mentioned, 2 open calls were offered within the project in the, let's say, first phase of the project, and was targeting the highest quality experiments that were provided by European SMEs. So in total, 42 experiments were selected through the process, were supported by funding, and are including 132 partners from 22 EuroHPC GEO member states. You can see on your right-hand side the map. So all these darker colored countries are actually partners of the experiments. We are happy to say that 62% of organizations are small and medium-sized enterprises, which are addressing the business challenges, as mentioned, in various industry sectors, but the focus was put on manufacturing, and 57% of all experiments are dedicated to this sector. So, as mentioned, experiment is actually, let's say, up to 15 months long process in which experiment partners, which gained the consortia within SME, HPC provider, or some other technology provider, domain expert, and some other type of, let's say, partner contribute to address properly their challenge. And as soon as experiment is successfully concluded, it becomes a success story, bringing the business benefits, highlighting, and of course, inspiring other wider community. So in the first tranche, we have 16 success stories already produced. You are really invited to visit the website or our social media. You can find all these materials there. And also we published the first success story booklet. It is also available in the e-format on the website. So our colleague Lucille already provided also the link in the chat, so you can easily reach it. And now we are actually in the phase of producing 26 new success stories that will come soon, so will be published soon. And meanwhile, we are working on 5 webinars. So today is the 3rd webinar, and 2 more are upcoming, where will be the success story actually primarily presented to public. So enjoy all these presentations.
Good morning. I'm Francesco Sabbarese, machine learning engineer of Youbiquo, and today I will introduce you to the experiment number 1107, called Handytrack, which is related to hand gesture generation, detection, and tracking. I will present the technical aspect while my colleague Valentina Senatore is going to talk about Handytrack business evolution. Okay, in this presentation we will cover the following key points to address the challenge at hand and present the proposed solution. We will begin by examining the challenge we are facing. We will delve into its details and discuss the difficulties it presents. Next, we will explore the objectives we have set to overcome this challenge. We will then introduce the proposed solution and how this can address and resolve the challenge. Subsequently, we will delve into the main outcomes we expect to achieve from the project. And lastly, we will discuss the expected impact of the solution. Okay, the challenge. End tracking and gesture recognition are critical components of AR experiences. Technology, and they allow us users to interact with virtual objects in a natural and intuitive way. To make end tracking and gesture recognition truly seamless, there are two main challenges that need to be addressed. The first one is low latency. AR experiences should be smooth and responsive, so any delay in end tracking or gesture recognition can significantly impact the user experience. The second one is the accuracy and the robustness in detecting end gestures in different scenarios in the shortest time. Okay, on the other hand, there are also two main business challenges to consider. The first one is the fact that most of the solutions are hardware dependent, and the standard products are calibrated toward the detection of one end at a time. Furthermore, currently on the market there are predefined number of recognized gestures, and training on undefined gestures requires custom solutions and are expensive in terms of time. Okay, now let's delve into the specific objectives that we aim to achieve with this presentation. Our first objective is to create a comprehensive video dataset consisting of diverse end gestures. This dataset will serve as a foundation for the training of our machine learning algorithm, enabling them to accurately recognize and interpreting gestures. The second objective is focused on developing a software library that leverages machine learning models. This library will facilitate real-time tracking and seamless recognition of dynamic end gestures, ensuring an intuitive and responsive user experience. Okay, we aim to harness the power of high-performance computing to expedite the training process of our machine learning algorithms. To enhance the accuracy and robustness of our end gesture recognition system, we will employ several and multiple phases of transfer learning or fine-tuning. I don't know. I am sharing the presentation. You can see the presentation?
Yes, we see it.
Okay, okay. Okay, we have also the accuracy in gesture recognition greater than 95%. And additionally, we aim to optimize the efficiency of our system by minimizing the time required for gesture recognition. Our objective is to achieve a time to detect of under 2 seconds, enabling near instantaneous response to user gestures. Okay, let's now take a look at the architecture of the solution. In this slide, you can see an overview of the different components that make up our system. In the top left corner, we have the dataset generator component, which involves capturing gestures using a generic camera. This captured gesture are then used to generate a dataset. Next, the generated dataset is sent to the high-performance computing environment, where undergoes its preprocessing phase and then is used for training our machine learning models. The HPC infrastructure provides powerful computing resources to expedite the training process and improve the overall efficiency. Once the models are trained, we move on the end tracking and the gesture recognition components, and the models are carefully selected and integrated into our system, enabling real-time gesture recognition and tracking. Let's now explore the gesture capture and dataset generator component. In the gesture capture component, a generic camera is used to capture a video sequence containing the gesture performed by the user. Next, we employ the Google MediaPipe ANS library, which is specialized in extracting and joins from video sequences. This library analyzes the gesture video and extracts the skeletal structure of the end over time. Moving on the dataset generator component, we employ a technique to augment the dataset by reproducing the same gesture with the translation, spatial translations, and the rotations. This augmentation process allows us to introduce variation in the end positions and orientations, enabling our machine learning model to generalize well with different end configurations. Additionally, we reproduce the same gestures in different environmental conditions and varying the chains, for example, varying the chains and the light conditions. Okay, through the dataset generator, we create a large and diverse dataset for training our machine learning models through the HPC environment. In this slide, we analyze the role of the high-performance computing in the solution. In the dataset management component, dataset undergoes preprocessing to extract and joins from the raw data, obtaining a fixed length temporal sequence of joints, ensuring that the data is in a valid format for the training of the machine learning algorithm. Moving on, okay, once the dataset is preprocessed, it is split into three subsets: the training set, validation set, and the test set, in order to train and evaluate models. Moving on the training management components, the machine learning model are trained using the training set. So the training process involves adjusting the model's parameters and hyperparameters to optimize its performances on the given task. The validation set is used to fine-tune these hyperparameters, ensuring that the model generalizes well on unseen data. Once the models are trained, they are evaluated using the test set, and this evaluation step allows to assess the model performance and measure the accuracy and effectiveness in recognizing end gestures. Now let's discuss the user application component, which focuses on the deployment and the usage of our machine learning models across various devices. The versatility of our system allows it to be seamlessly integrated into different devices, ranging from laptops, smartphones, and AR glasses. Once the system is deployed, it enables frame-by-frame tracking of the end joint and is designed to recognize both static and dynamic gestures performed with one and two ends. Let's analyze work done, and in particular the task one, in which we focus on the software algorithm developed for gesture recognition. Our approach involves breaking down the complex problem of gesture recognition into two simple tasks. The first one is end tracking over time, identifying end joints, and the second is the gesture recognition based on the detected joints. The input to the system is a video sequence. So using the MediaPipe library, we process each frame individually, extracting the end joint and creating a fixed length temporal sequence of joints. The preprocessed sequence of joints is then inputted into the gesture recognition model, which predicts the most probable gesture based on the given input. We further enhance the gesture prediction by aggregating the predicted gesture over a temporal sequence, and by extracting the most frequent gesture from this temporal sequence, we increase the reliability and the accuracy of the overall system. For the task 2, we focus on the parallelization of the code on the HPC architecture to enhance the efficiency of our training process. Due to the compatibility of required libraries such as MediaPipe with the architecture of the HPC environment, we run the preprocessing and the training into two distinct environments. The first one is the DGX, and the second one is the Marconi 100. The table offers a comparison between the two architectures of the machines. For the training phase, to achieve the parallelization, we use ORWOOD, which enables us up to scale the training script based on TensorFlow and Keras from running on a single GPU to leveraging multiple GPUs in parallel. The dataset is divided or sharded between the available GPUs. So each GPU trains the same model on the chunk of data stored in its memory. The optimizer shared among the different GPUs performs an average of the gradient computed by each GPU before proceeding with the subsequent epoch. A comparative analysis was conducted to assess the time performance of the data augmentation software and machine learning training for end gesture recognition in both no HPC and HPC environments. The table above shows the feature of the two environments used for the experiments. For the data augmentation procedure, we evaluate the time required to generate a dataset starting from 10 gestures performed in 10 different poses using a multiplication factor of 5,000. The table below shows the results, highlighting the time reducing in the HPC case. For the machine learning models training, we evaluate the training time with the 10 execution running on no HPC and HPC environments. The graph on the right highlights the experiment that achieved a lower training time in percentage compared to the same experiments conducted on the other environment. It is possible to observe how the training execution is more efficient on HPC environment when the condition P1, P2, and P3 are verified. The conditions are shown in the table, and so P1 is the batch size greater than 256, a number of neurons greater than 100, and a learning rate less than 0.001. Okay, the benefits that we achieve with this project are the following. The first one is the improved training time. With HPC, the training time for neural network can be reduced by 18% compared to the traditional computing resources. This can result in a faster development and deployment of end gesture systems. But the second one is the reduced cost. HPC can reduce the cost of end gesture of generation of end gesture dataset by up to 99%. And this can make it easier for companies and individuals to create and train custom end gestures. Natural user experience, because dynamic end gesture model allow AR devices to provide a more natural user experience than the static ones, and an unlimited end gesture dataset, because HPC can allow for the creation of an unlimited end gesture dataset, which can be used to address several domains and the market segments. Lastly, the main outcomes that we achieved. The first one is an enhanced user experience. Implementing our end gesture recognition system offers the opportunity to provide a more intuitive and immersive user experience. By enabling users to interact with the application and devices using natural end gestures, business can enhance user satisfaction, engagement, and overall brand perception. The increased efficiency and productivity. Incorporating end gesture recognition, customers can streamline workflow and increase productivity in various industries. For example, manufacturing and logistics, workers can use gestures to control machinery or navigate through complex systems, reducing manual input and minimizing errors. This leads to improved operational efficiency and cost savings. A competitive advantage because adopting end gesture recognition system can give business a competitive edge in the market. Offering innovative and user-friendly interaction methods can differentiate a company products or services, attracting new customers and retaining existing ones. This can lead to increased market share and revenue growth. Expanded market reach because a device-agnostic and gesture recognition system allows business to target a broader audience. By eliminating the need for a specific hardware, the system can be integrated into existing device and platform, reaching a wider user base. This expanded market reach opens new business opportunity and potential partnerships. And lastly, improved accessibility and inclusivity. And gesture recognition can provide enhanced accessibility for individuals with physical disabilities or limited mobility. By enabling gesture-based interaction, business can ensure inclusivity and cater to a larger customer base, fostering a positive brand image and meeting regulatory requirements. Now, Valentina, you can continue.
Yes. Okay. Good morning, everyone. I'm Valentina Senatore, Business Development Manager of Youbiquo, and today I would like to introduce you to the evolution of the experiment, of ND-Track experiment. Within the experiment task 3, we have worked on the experiment business plan, thanks to which we have developed a beta version of ND-Track called iGesture. And basically, we have converted the experiment into a potential product. And now I would like to show you a mock-up video to present the solution. I hope it will play.
AI Gesture is the solution that solves these problems entirely in the cloud. AI Gesture is the platform that allows you to record a video of the gesture and subsequently generate a synthetic dataset. This approach increases the quality of the recognition and reduces time and costs for the production of the dataset. The use of AI Gesture is simple and intuitive. A video of the gesture is recorded. The generation of the synthetic dataset is requested. It is possible to set some parameters, such as the number of videos to be generated and in how many settings to generate them, and then proceed with the generation. After a few minutes, you are ready to download the synthetic dataset to use it in a neural network training process. Now you can train your neural network for gesture recognition. Create your own set of gestures quickly and easily for applications on interactive displays, AR/VR headsets, for sign language recognition, and much more. AI Gesture, the solution for neural training.
Okay, so basically, a gesture comes out and the track thanks to a lean canvas model that we have applied to develop our business plan. And we have come up with a, let's say, a pitch deck structure. And I will quickly show you how we have approached the problem. So we have started from identifying the pain. The problem that we have identified affects software developers that programs IR application for IR devices. And to program touchless and gesture interaction, our developer needs to have available an unlimited recognized gesture in unlimited scenarios, and it needs to work with software solutions that are no device dependent. Moreover, we have discovered that it needs to work with the detection of two hands simultaneously, as Francesco has mentioned. For this reason, we have come up with an hardware agnostic AI platform calibrated towards the detection of two hands simultaneously, which consists in a synthetic data augmentation framework that processes unlimited dynamic gestures on which we train our neural network. Thanks to the solution we have developed, our platform can be easily converted into a no-code and gesture configurator, which is accurate, fast, affordable, and user-friendly. We have also worked on the market size. We have discovered that in relation to the global gesture recognition market, the total available market in 2020 was 2.3 billion. And in 2030, it's expected to be around 16 billion. While targeting only Europe, the serviceable available market will be 2.6 billion, from which we have calculated our obtainable market around 74 million. We have also worked on the competition, and we have developed a competition matrix that shows that big players like Leapmotion are hardware dependent, while startups like Manomotion and Banuba have a fixed number of recognized gestures, and for this reason, they have low scalability opportunities. iGesture targets basically B2B and B2B2B markets, and we have also worked on a business model which is based on two revenue streams: a pay-per-service model for the generation of a new data set, and a paper license to access all the gesture data set available on the platform. As I've mentioned before, we are piloting a beta version of the solution in 4 different ecosystems in Birex, which is one of our partners in this experiment, and we use it to interact with robots. In Televest, Microsemi, and Kleeman, we use it on production line to interact with the quality assurance architecture, which is within a project Horizon 2020 called Optimi. Furthermore, we deployed iGesture on the Huawei cloud during a European competition sponsored by Huawei, in which we won the second prize. Thank you very much for attention.
I will present today the project experiment HyParallel. It is about high performance reliability computing. I'm the coordinator from the Austrian company Pumacy GmbH. And we worked in very close collaboration with 2 end users. One was the Slovenian factory KLS, and the other one was the German factory Matec. We had in the background an HPC center. It was from Germany. It was our sister company, Pumacy Technologies. Yes, the challenge. What was the challenge? If we look to production of parts for metal, plastics, rubber, and so on, we have the problem that if we have a long time production, we have 2 phases where it is a little bit different. Because if we start, there is not all clear about, we have to optimize the production, and so we have more failures in the first phase of the production. And if we go over the time, if you see here the picture, then the last phase is also a little bit critical, because there are wear out failures, and during the process we have a process of fatigue, and so it is important to have a really deep look to the reliability of the production. And so we talked to two of our customers. They already do that. They collect data, but today they have really problems. They have had problems to learn from that data they have. And so we started this project. We divided it into two use cases because the companies are a little bit different. The first one is KLS from Slovenia. It's a medium-sized company with around 200 to 250 employees, and their production is really highly automatized, and it's a serial production, and they have highly automated. That means they have more than 100,000, sometimes more than 1 million parts. And so it is very important to have a really seamless integration of all machines of the production lines. Their products, you can see here one of this. This is a starter gear ring. It's mainly for the automotive, but also for the drivetrain. Also, there are a lot of not only metal working machines here. If you see the picture, that's a picture of the machine hall. They are coupled in a process, and a robot takes a piece from one machine and put it to the other machine, and so it's really automatized, and you don't see a lot of workers in the factory. The problem is that the high machining frequency demands really a continuous production, and we have enormous load on the machines, and so it's important to have a look that the machines can run a long time than only 7 hours as today. A little bit different is the use case of the second company. It's Martech. It's a rubber company in Germany. Rubber is usually not that product what is in that high pieces. There are a lot of components or parts. If you see the bellows here on the upper part of the picture, where you have a small batch production of 10,000 or 25,000 parts. Not only bellows, you can also find such products as gaskets and membranes. We call that together technical molded rubber parts. To produce that, Martech today uses a combination of semi-automatized plastic processing machines on the one hand, and also two, as you can see here, this Desma machine. It's a really fully automated process which goes in this machine. The problem is here that they have a special material peculiarity because the rubber shrinks, and it's a two-stage manufacturing process where you have to heat the material. So the approach was that we Pumacy developed, and we have a data analytics platform. It's called Plexalytics. It uses so-called search-based applications, and we discussed how we can get the data of the company into our SBA platform, how we can use machine learning to recognize these data, and yeah, what can we do to accelerate this process, because we don't own an own data center, and so we needed a third party which does the HPC. Yeah, what we developed was a 5-step procedure. It's only a small visualization of that. It's not only machine data. You can also see here a rubber machine, a plastics processing machine, or you can also imagine that there are more than one machine. You can have here a whole production line, which are bringing the data into a special database, which is placed at the factories. And then we collect the data and bring into our special approach. It's approach with use activity and process mining. In the background, we use machine learning. And after that, we give the end users models where they can see, is it a good one or a bad one? Do they have any failures within their production? And maybe what can they learn from their failures? Yeah, I will describe the process, what we operated here a little bit deeper. That's the first step. We had, yeah, for some machines, we have had an API. That is the easier process. We brought it to the SQL, to an SQL database, and then we have, we call it the raw data from the machine. The compressed data was 60 gigabytes around, and after extraction, it was 500 gigabytes. But you have taken into consideration that is only from one machine. And if we put together more than 10 to 20 machines within a production lines, we get a little other figures of that. The second challenge we had, that not all of the machines delivered the data we really need. So we used sensors to collect data we don't have, maybe frequencies or sometimes temperatures, and then we bring it also to the database, and so we enrich this data with additionally data from the sensors. The process of the data analytics started with this, we call it chunking. That means that we divide the data sets into smaller chunks, so we are able to easier compute this data models, so we have at last a chunk size of 10 gigabytes for all around this data we collected here. The third step was that we have to convert it into a data frame. That means that we have to clean the data. Sometimes we have delimiters, we have the problem of none, not any number. That means that we have to remove this data, and if we are ready, then we convert it into such a data frame for the next step, because we really need that clean data if we want to start with the timestamps. Timestamps mean we have a special time step of the machine where we overview a special variable, maybe a frequency. And if you can see that here, we plot this timestamps, and then we go a little bit deeper, and that is the end of the raw data we have. As you can see, it's difficult to see that directly from the time data to recognize here any failure, and so we start with the it's almost the last step for the computation. It's a fast Fourier transformation that it's very computing intensive process, but it helps us to find frequencies which are interesting for us. And if we have here any peaks, we can compare that with the history of the machines, and we are able to find out will there be a failure in the next hours, or is there a special problem? We are able to understand what kind of failure is it, and so we learn from this data here in the example by using frequencies. Yeah, it was an HPC project. I have seen here a lot of presentations with simulation. Yes, I know simulation is much more data intensive, but for us, it was really also a data intensive project because the companies, the factories can't wait a week as they have done that before. The process goes so that they collect the data over the shift, over the day, and after the day they bring this compressed data to the HPC center. And so we are able to enrich the data to do our index-based, search-based application operations, and after that the machine learning process. And so we are able to do that over the night. And so in the morning, every company can start with their learnings from the night. That was for both companies really helpful. And for us, it was the first time that we can present that not only for big companies, because they usually have that computing power in-house, but also for small to medium companies. Yeah, we to get an idea about outcomes and business impacts, we asked both companies to give us some feedback, and I think both companies agreed that they are able to use this process also in future, and because they now can do this HPC computing with a partnership with a software as a service-based model. And so we plan to introduce this product within the next months into their production. The other thing is that we have to deploy that process also for the other production lines. The end user feedback, what we get is now they can produce for the highly automatized serial production full 8 hours instead of 7 hours before. That means they can survive, all machines can survive the whole shift of the workers, and that's a really big step. And if you see here, that's the productivity. It's not only, it's 40%. Yes, that sounds small, but it is really high. Because now they don't have to interrupt the production between the shift directly in the shift. They can wait if the shift is ready, and then they can take the service processes of the machines. They want to extend the yearly capacity at 150,000 parts by using that from currently 1 production line, and at the end of 2024 we will have 6 production line in operation then. Yeah, exploitation for. I'm the manager of the technology provider, Pumacy, and for us was the question, what can we do with these experiments? For us, it's really important that we now have first time a product where we can do where we can support the data analytics not only for enterprises as we have done it before, but also now for small to medium factories by giving them a combination of our data analytics service within a software as a service model in combination with an HPC center service, so that they can do their data analytics also for that big amount of data spaces they have. We want to integrate within the next months our own our experiment result into our search-based application platform Plexalytics as a special module, and meaning that a customer can order that within the acquisition process as part of our overall service. And yeah, I think we will need some more months to bring both customers into operation, but after that we will start the acquisition for further customers in metal and plastics industries all over in Europe. Just we right start in the Central Europe, and I think we have also taken it into consideration that it is not that far away to transfer these use cases also to other industry sectors, not only other industry sectors, but also to other kind of manufacturings. But because the ring gear production, maybe for metal parts, that's only one very small part for a whole car, and there are a lot of parts where we can support smaller to medium factories in future.
Okay, so thank you, Mr. Chairman. So I will try to introduce and discuss our project, which is an application of HPC and AI assisted processing for the water cycle management from satellite data. First of all, I would like to introduce the team of the project. That just a moment. Try to remove this window. That is built by Aresys, which is a service provider. We have experience in creating software and services for satellite data processing, especially on synthetic aperture radar data. Then there is the University of Rome, La Sapienza, which is a world-renowned leader in and expert in optical image processing and geomatics. Then we have Sorical, that is the end user for this project. Sorical manages the 2 reservoirs that we targeted in the project, and they serve fresh water to nearly 2 million people in the south of Italy. And finally, we have Cineca, which is the Italian NCC, that provided both expertise for the exploitation of the HPC capabilities and the HPC premises. Motivation. I think that these 2 images that are the 2 sides of the same coin explain at best what are the motivations of this project. So we had in the last years both water shortage and periods of droughts that are interspersed with extreme weather conditions and extreme events. So the current management of water resources is really a critical issue in any European country, especially in Southern Europe, as we are based in Italy. So the objective of the project is dual. We have a primary objective, that is the development of a smart monitoring service that take advantage of HPC to process optical satellite data and monitor the surface extent of man-made reservoirs, so to allow smarter and continuous management. Then we have a secondary objective, that is to build an exemplary success case for the application of HPC to Earth observation data. I will discuss this later, but it seems counterintuitive, but it has a lot of meaningful reasons. So the first objective was targeted by selecting 2 reservoirs in the south of Italy, Diga del Menta and Diga di Alaco, that are managed by Sorical, the end user. You can see both of them in the images. And by analyzing satellite optical images and computing by processing the extent of the water surface during the seasonal variations, to make a living map living tomographic map of the reservoir itself. And the secondary objective. It is well known that for geological studies, so looking below the Earth, HPC is already something that it is currently used. I have some example from Eni, Saudi Aramco, Total, Petróleo Brasileiro. They have, as private owners, the best HPC facilities in the top 500. So, for instance, Eni at number 13 is the first most powerful HPC in private hands. However, for satellite data processing, let's speak about European Space Agency, HPC is still not something used nowadays. They are just using basically cloud computing, no GPUs, and so on. So, in our opinion, HPC in the next year will bridge the gap between the increased your processing requirements and the new envisioned data exploitation opportunities. In the next years, small swarms of satellites will be launched, both from ESA and from private entities. So there will be a change, a total change in the downstream space market. So satellite optical images play a key role in identifying water variation over time. The big advantage is that they do not need any additional apparatus. It can be done at a negligible cost because, as an example, the data we used, the dataset we used, that is from Copernicus Sentinel-2 constellation, data are freely available. You have a revisit time of the constellation that is made by 2 satellites currently of 5 days. And the most important advantage is that you start and you want to monitor a reservoir today, you do not only have the ability to monitor in the future, but you have all the historical observation from June 15. So you already have historical time series by free. That is really a big advantage of this type of observation, in contrast to any additional apparatus that, if put on a reservoir or on a dam, it will give information only for the future, not for the past. We have a major challenge in this case to overcome. The resolution of hyperspectral Sentinel-2 images is limited. In particular, it is 10 meters for visible, red, green, blue, and near infrared. So what we have done during the project is define an artificial intelligence-based super resolution approach that can overcome this limitation, but is the real reason that we require HPC in this case. So just discussing the solution that after my previous words is really straightforward. So you have a time series of Sentinel-2 images over time at 5 days. You have gaps because not all the passes are usable because of cloud coverage, ice coverage, because you are passing during the night, and so on. So you need to do patching, but also a specific selection of the images that can be obviously done automatically. Then we have a GPU-based, deep learning-based super resolution approach that give us a 4-pair resolution. That means we are going to nominally 2.5 meters of resolution, and from a practical point of view, we measured 4.5 meters for these 2 reservoirs. Then on the super resolved images, we estimate via spectral index the water surface, and after having extracted the water surface, we reorganize from time to height above sea level, and so we have a model of the reservoir that can be modifies over time. So it can be different from the planned construction model that may have a lot of years and may have changed. So just a few words about the HYSY super resolution that we put in place. What it can be sketched usually is that in conventional processing, you have software engineers and developers that develop some code, some algorithms, and this is a human-intensive activity. When you put a deep learning approach, you substitute your developers with data scientists, because there is the centrality of the training dataset that basically substitute the code development phase. This building of the training dataset that really put some effort and may harm the final quality of the solution is human intensive, because you have data scientists, not more software engineer, but you have data scientists, and is computationally demanding, especially for the training phase. Then in the inference, you have no problems. We have gone a slightly different path in this case, and in our solution, we selected a different deep learning approach where we do not need any training data set. So basically, it's no human intensive. We do not have really a limitation on the building of a training dataset, and it is the reason because we had only 2 reservoirs as targets in our experiment. However, the drawback is that it is more computationally demanding, both in training and inference phases. Just a few more words. We have chosen a slightly modified version of deep image prior that have no need for any training dataset. Basically, you do not have no training and no inference. Training and inference is the same phase. It is performed on a single image at a time, so it is the approach is embarrassingly parallel, so perfect for HPC. And however, you have a mandatory need for a lot of computing power for each processed image. But the results speak by themselves. You have on the left the industry standard, and on the right the deep image prior. So it is visually clear the improvement that you can have in this case. That is, in our opinion, one of the key points of the outcomes of the experiment. So we were able to trade human-intensive activities with computing power, and the solution is really highly scalable. So it is really a win-win situation for HPC in this case. Some notes on the HPC usage during the experiment. So we used Marconi 100, strictly GPU nodes, and we used 4,000 node hours of GPU nodes. And as GPUs, the real need of GPUs has been identified really early during the experiment, we really did not need to do a lot of comparison of GPU versus CPU. So basically, we have not exploited any core hours on Galileo 100. One of the, let's say, drawback, but it is a requirement by design, is that the result of the experiment, that is a service, is this HPC for reservoir management, that will be provided as a software as a service, we need the access to HPC resources for each image we want to process. That is, in my opinion, still an advantage. We are trading people, hours, with less expensive GPU hours on HPC nodes. Just to, as a final word, just to make a small comparison, the processing of full historical dataset for a reservoir can take few hours on a good group of parallel nodes on Marconi 100 that became GPU, that became an equivalent of 15 days or more on the same GPUs, but not in a parallel fashion, that are roughly 15-20 months of equivalent processing on a single CPU workstation. That is quite astonishing as numbers. So going to the outcomes. So now we have a monitoring prototype service that Aresys can offer to customers that are involved both in freshwater management cycle as the end user of this experiment, and to hydropower, to players in the hydropower renewable energy sector. We have already contacted them. We have contacted the Italian leader in the hydropower energy sector, that is Enel Green Power. Then, how can Aresys, that is SME consulting in the space economy sector, put in place such a monitoring service that need to be scalable? We need to source on-demand computing power from HPC provider. And only in this way, we can make the business suitable for us. And I think that it can be seen as general results for SMEs in innovative sectors to compete with bigger players. So, final impact. Why one should activate a similar monitoring service? Because it is a way to lower the overall monitoring cost of and gain new knowledge on the reservoirs, so on their true assets. We estimated, we did our homework, and we estimated that in Europe, the overall market of monitoring for man-made reservoirs, so dams, is around 200 million euros. As an example, for Sorical, this translates in 30 kilo euros per year of cost savings and possible new idea of exploitation of the assets. We already built a dedicated group within Aresys to exploit optical observation data with 3 specialists with 2 new hires. So it's something that we are really already playing on. And we started as Aresys as expert, especially in the radar sector. So we expanded into the optical EO data. That is something really interesting. Also because in the really few next years, there will be a new Italian constellation, which is IRID, which has optical satellites in low Earth orbit that will have potentially better resolution performances than European Space Agency Copernicus Sentinel-2 satellites. There are a couple of weaknesses, however, on all of these solutions. One that is something that, in my opinion, is sometimes general, is that there are a lot of regulatory obligations, laws, that can prevent or slow the adoption of innovative ideas and concepts, because you are obliged to follow some rules also in measurements that, as they are quite old, cannot be automatically cope with something like satellite observation. And then another one that is more technical. The applicability is not general, but is site-dependent. You need, obviously, Sentinel-2 data availability, but coverage is nearly worldwide, so it's not a big issue. But especially, you need that the reservoir seasonal filling periodicity and the amplitude of level variation, you need that they are compatible with the observation. So if the reservoir is all the time at the same level, you cannot do anything with such a technique, but then you even do not need such a smart monitoring. You are in a grace situation that with no threats of droughts or other extreme weather conditions.
Thank you for the opportunities. I'm Alessandra Truppi, the coordinator of the project HYSY, Multi-Phase Modeling of Nanofluid Hydronic System. I'm a PhD Senior Chemical Scientist of TCT Nanotech. The partner involved in the experiment, in this experiment, are as follow: the end coordinator and the end user is TCT Nanotech, a division of TCT, an Italian company with the headquarters and manufacturing site in Brindisi. TCT Nanotech is the active in nanotechnologies, specifically in heat transfer nanofluids, such as HTF Compact, the product of TCT Nanotech. Cineca is APC Center, is the largest Italian supercomputing center with an APC environment. And finally, in this experiment is involved as technology expert SETMA, is a Italian private research center specialized in advanced design technique and numerical simulation and in development of software for industrial applications. What is the object of the project? The nanofluid are a promising nanotechnology to improve the heat transfer efficiency in hydronic systems. This system contain a liquid as a medium to transfer heat, and the adding nanoparticle in a heat transport fluid, there is the possibility to increase the thermal conductivity and conductive heat transfer coefficients with a more efficient exchange. The problem is that the nanofluid performance depends on a very high number of variables. as necessary as a consequence, an expensive trial and error approach is typically necessary to set the nanofluid. The goal of this experiment is to optimize the nanofluid design by using advanced simulation technique and HPC resource, maximizing the heat exchange in the system while minimizing pressure drop, high cost of the production stage, and the difficulties in preparing stable nanofluids. What is the challenges in this project was to set a robust numerical model to able accurately simulate the nanofluid behavior in a very short time, some hours, thanks to HPC resource supporting the design and optimization team of Hydronic System in TCT. And to obtain the optimized solution, maximizing the nanofluid performance and consequently improving the competitiveness of SMES as TCT, taking into account all the involved parameters, material volume as material, volume fraction, size, particle, base fluid material, and operating temperature and flow rates. The solution and the HPC approach, in this case, the experimental activities of the project are divided in 4 technical tasks. Task 1, definition of the input and output requirement, in particular all the input and output requirements of the nanofluid and complex plate heat exchanger have been collected by TCT and SETMA. In task 2, setup of the numerical model, in particular setup of a thermofluid dynamic numerical model able to analyze the nanofluid behavior and the effect of different parameters on the heat exchange performance of hydronic system. In task 3, in the numerical model has to run to the HPC resource of Cineca, and in order to obtain the definition and validation of all the procedure using the HPC resource. In the task 4, circular numerical analysis and the results evolution of HPC basic platform. In this case, the nanofluid properties were optimized for the selected plate heat exchange using the Cineca platform and the OpenFOAM code. And finally, the benchmark tests were carried out on the HPC system in terms of computing time reduction. In task 1, TCT, supported by SETMA, has collected all the input and output output requirements of a nanofluid for hydronic system, and has selected a critical plate heat exchange component for hydronic system and provides SETMA all the input necessary to set up the numerical models, such as 3D card geometry, structure, material properties, has conductivity, specific heat capacity, and usual operating process parameter as flow rate, external temperature. In this slide, here it's reported the storyline of the setup and validation of removal of numerical model. In a primary step, the model was applied to a simplified test case, linear pipe. This test was carried out working in a single and double phase model in commercial code versus open form. And finally, it was obtained the experimental validation. In a second step, the model was applied to a complex test case, heat exchanger. In this test was carried out working in a double phase model with commercial code and obtained the experimental validation. Successively, in this case, complex test case, was obtained the calibration of open form single phase model with the double phase model in the commercial code. And finally, the nanofluid optimization was obtained using open form single phase model and finally experimental validation. So, in the first step, the numerical model was set up and validated by comparison with the literature results using the license commercial code MSC. The schematic setup of the experiment used for this work is shown in figure. The part of the rig which is relevant for this work consists of the long carbon steel pipe. This. And with the help of the electrical power unit, the pipe section could be charged with the different heat outputs. During the experiment, the wall temperature of the pipe could be measured using 4 thermocouples, each at 8 different positions along the pipe. And the obtained numerical results we compared with the values in the article, and we have obtained a very good agreement of the results. Another validation procedure was carried out using a linear pipe at laboratory scale developed by TCT with double phase. This phase allowed to gain confidence with the open source, so applying this kind of flow. In particular, in this experimental validation, the base fluid and nanoparticle are modeled separately as 2 different phases. In this case, TCT used a nanofluid which consists of 50% of water, 45% of ethylene glycol, plus 5% of HTF nanofluids. A check was carried out on the temperature values of the nanofluid in output from the heat pipe. Comparison among experimental data and numerical results carried out using a commercial code MSC Tetra and an open source code OpenFOAM. As can be seen from these temperature values, we obtain a good agreement. The next step was to model a complex test case with the selected plate heat exchanger of in task 1 with commercial code. In this case, we have heat plate exchanger that consists of a series of 10 parallel metal plates that are placed on above the other to allow the formation of a series of channels for fluids to flow between them, exchanging it. The space between two adjacent plates form the channel in which the fluid flow counter current without mixing. In fact, in late outlet holes at the corners of the plates allow hot and cold fluid through alternating channel in the exchanger, so that a plate is always in contact on one side with the hot fluid and the other with the cold fluid. The main difference from the previous simple test case was the need to include the conjugate heat transfer between liquid and solid, which led to the use of different solver of the open foam suite. The new solver was only transit with a lot of problems in terms of unstable flow and diverging results. As a backup approach, this complex heat exchanger was analyzed using the dual phase model in the commercial code, which was validated through the data provided by TCT, as reported here. After that, the same model but with a single phase fluid was set up and calibrated in open foam. It's a two-step procedure. We start from the nanofluid components and the thermophysical properties. Then we compute the thermophysical properties of the nanofluid using a mixed dual single phase and iterative procedure, and finally the nanofluid are used an input to the heat exchanger simulation, which will be carried out using a single phase solver. We finally set up the numerical model of the heat exchanger in open foam. It uses a steady state solver able to solve the conjugate heat transfer. We were able to obtain the same results of the more complex dual phase commercial model. This model was used on the Cineca grid for our study. Moreover, we had access to the Galileo 100 HPC system of Cineca. We were able to transfer data from and to the storage areas. And typically we use to upload the mesh data on the cluster and retrieve the results files from the cluster to locally post-process them. Open foam calculations were submitted using a script which allow to allocate cores on the cluster and using its scheduler and executing the job in parallel. The resource usage has always been monitored via the provided utility. We executed a scalability test on the Galileo 100 cluster to establish the convenient number of core to allocate for each run. We consider the heat exchanger model of about 10 million cells and executed the simulation varying the number of allocated nodes from 0.5 to 8 nodes which mean from 2024 to 384 course. Science on Galileo 100. We have 48 course for each node. We found no considerable time saving going from 4 to 8 nodes. So in the end, we choose the 4 nodes configuration, which allow to complete a single simulation of the complete heat exchanger model in about 2.5 hours. We've just just make a comparison. The same open form simulation on a good workstation of SETMA would have required no less than 60 hours to be completed. We executed a parametric study varying the flow rate and flow rate of the working fluid into the heat exchanger and the concentration of the nanoparticles. The evaluated output were the exchange and the pressure losses. The graph in this slide summarizes some of the results of the simulation, represents the heat exchanged versus the fluid flow rate, which differ concentration of nanoparticle from 0 to 7.5%. So if we fix a specific flow rate, we observed rates of the exchanged heat due to the increasing conductivity of the working fluid. We could reduce the exchange area and optimize the geometric design of the heat exchanger, which was not the goal of our activities. Instead, if we choose a specific level of exchanged heat, we can observe that raising the nanoparticles concentration, we can lower the flow rate. In this case, we pass from a flow rate of almost 25 liters per hour to no more than 10 liters per hour. This has to effect on the energy consumption. We should pump less fluid, but with an increased viscosity, which means more load losses. This means that we must optimize the nanoparticle content, balancing between two different necessities, raising it to maximize the heat exchange and lowering it to minimize the pressure losses. So we have elaborated all the data obtained from the simulation. We were able to relate the energy variation with the nanoparticle concentration. As you can see, we obtain a good fit. In fact, the reconstruction curve passes from the origin as we expect to have zero variation with zero nanoparticle content. The curve in this case has a maximum which represents the best balance between the two effects I spoke before, and the optimum nanoparticle fraction is of about 5%, which gives us an energy saving of about 9%. After several studies, TCT Nanotech found out that the best solution in the nanofluid flowing through the evaporator for the chiller, and to do so the circuit of the testing rig have been inverted. The chilled nanofluid flow in the chiller side, and the water flows in the heating circuit. In this case, we have obtained a good experimental validation, as reporting in this number. So, what are the business benefits by using HPC resource and advanced simulation technique? TCT expect to reduce design cost by 50%, material waste by time to market by 66%, material waste by 80%, and reduce the energy power for its customer by 10–25%. SETMA expect the success story lead to new R&D project and consultancy service to other SMEs. And finally, Cineca aims to become TCT provider of HPC resource and to exploit this success story to attract new customers. Finally, the benefits of this project are expected outcomes and revenues of HYSY experiment, creation of a partnership among TCT, SETMA, and Cineca for the exploitation of the experiment results and the future collaboration, enable HYSY to advance the HPC platforms, improve visibility on the market and the networking opportunity, and finally, but more important, acquire new knowledge on the nanofluid optimization to be used in new R&D project and consultancy service. In particular, for this project, HYSY results consist a great opportunity to TCT Nanotech because it was found and validated a robust approach to reduce the development time and cost of nanofluids and to improve the quality of a new hydronic system containing nanofluids requested by its customers. Thank you for attention.